Hello, welcome back to tutorial number 2 of the JEPA architecture. Where we left was the calculation of this partition function. And so if you want to calculate your, if you want to finish this calculation where you want to have the probability of this distribution, you have to estimate the partition function. And well, as an engineer, what you will do is you can say, well, it's easy, just partition my space, the input space like X, and then I'm just going to do a sum. And okay, I have to calculate this exponential, but nowadays, we have very nice lookup tables or, very fast CPU calculations, so it shouldn't be that hard. And so, well, it seems all quite easy. The problem is that as you increase the dimensionality, even if you have a standard number of cells, this problem explode. And so let's have an example here where I essentially try to calculate this partition function based on the current CPU that is running on my Colab, and it's going to essentially give me an estimate of how long it's going to take to calculate different partition functions based on the dimensionality of the my input space. In this case, we have 2 dimension, and essentially how many bins do you have. And you can see that, okay, if you have something small, like you can do it within microseconds, milliseconds. But when you go to something like doing more serious or useful, it's going to take like many years. So even if you have a big data center and you want to process this kind of standard minist image training set, it's going to take you just an impossible amount of time. And so how people have solved this? Well, in the past, you have 3 solutions. So one is the contrastive divergence, which is a short, you're using a short MCMC chain to approximate Z, or you have the contrastive EBM, which is the one I'm going to show you now, which essentially you cancel zeta algebraically by comparing real points versus fake points. And then you have the JEPA approach, which you never sum over any space at all. So it sounds like magic. I'm going to essentially enable some imports here. And because we need PyTorch to calculate the gradient and the energy function. But first of all, let's create our simple data set. So this is like 2 blobs. If you're familiar with ML, this is quite common. In this case, we don't care much about the colors or the labels, but it's more about the distribution. So we have 2 Gaussians centered around 2, roughly, or was it 2.5? So 2.2, just to make it a little bit harder. And so what you do next, you define an energy model, which is an approximator. So you have a neural network of essentially 3 layers. Okay, and these layers essentially tells you how likely is an input to belong so how likely is X when you feed forward this one, you get a scalar number. Does this belong to the original distribution? Okay, and as you can see here from the output, you have a linear layer which just give you a number. There is no softmax, no sigmoid, just a number. And Adam is the optimizer, but you can use, I believe, everything else. I haven't tried, but feel free to try and let me know what happens if you use like another optimizer. And the point of this energy function is that you want to shape it in a way that the real data points belong to the low valleys, low in the energy function, but the points that don't exist, so out of distribution, should go up. So they should have high energy. And okay, so yeah, so you have this function which is totally random. And now the problem is, well, how do I choose these negative samples from, right? Because they kind of, well, they don't exist in my original set, and I have to sort of create them. And in a contrastive energy based model, we need points that can do this push pull. Okay, and well, people have tried before. I remember in my courses that, well, what about I just add random noise? Like, hey, let's just sample, just sample random noise, right? But the problem is that they will be too far from the data, and it doesn't work. And you can actually try. Maybe I'll do in tutorial 3 to see what happens if you just you don't use this equation. You just you just create now random noise. And this formula here is essentially the theoretical answer. So it's not a trick or a workaround, but it's a probably correct MCMC sampler derived from the physics of Brownian motion that you study probably in physics or statistics. And this is the kind of update rule, which is, well, it's simplified, but you have the the input sample, the step size, which it's essentially usually is called epsilon, and this is divided by 2. Then you have the derivative of the energy function alongside the input, so it's the gradient. And usually other things, so you have the square root of the epsilon multiplied by n, and n is the noise. So anyway, so this is kind of simplified, and this is designed to create these samples that they don't exist. And well, so whilst we have the equation, which you can find here, the problem is that, well, we have to approximate it because we're doing this numerically. And in this case, I'm using 40 steps of a fixed size. So the step size is 0.044, and you have 40 steps. And the reason why I do this is because I sort of normalize it so that if you multiply this, you notice there is a 4 and a 40. But yeah, so the point is you have to do this approximation. And well, the problem is, well, how many steps do I do? In theory, I need sort of, well, I know that it converges when epsilon becomes very close to 0 and the steps are infinite, but you cannot run this for infinite time. So you have to sort of decide, how long you want to run this. And you also have a clamp, which you should enable for numerical stability. And well, I was disabling them just to see what happens, and you can play with these things. So I'm using now the full function implementation. Okay, so then we train the EBM. When we start, we have a random energy field. So it looks like that. This energy function is totally random. As you can see, doesn't really match my data point. When I run this for 400 epochs with a batch size of 20, let's see what happens now, right? So, and I'm going to plot it every 100, so I should have 4 plots, or 3, depend on the last one. And you can see here that it sort of starts, the valleys are at the bottom, then it sort of goes up into like an horizontal band, and then it starts to squeeze in the middle, and then you have this kind of very two nice isolated valleys, which means that the algorithm has learned very well. And so, yeah, this is, as I mentioned before, this is contrastive learning. And essentially what you do, you have 2 terms, which is the energy, let's say, of, so where is the contrast? The contrast, you have the energy of the real points minus the energy of the artificially fake points. And then what you want to do is, well, you want to minimize this difference so that the real points go down and the fake points goes up. And you also need some regularization, which is useful to penalize the let's say the absolute energy values, because as we mentioned before, the energy function can be, well, infinite, right? You can have an infinite energy function, and so you need to have some regularization to penalize. Otherwise, like, these things can go between infinite and minus infinite, right? And so, well, this is this is the way you solve this. And now maybe you're asking, well, okay, this is great. Like, what, I don't know, why do we need JEPA, right? And so, well, there is kind of a computational problem here. Is that, well, so the way you do it, you sample the real point, you run Langevin for getting the negatives, you compute the contrast, plus you add the loss for regularization, you do backprop, you update weights, and then you repeat. So essentially, if you go back to this function, and feel free to play with this, is that for every iteration, it goes 40 times backward and forward. Right? So you do the forward pass, backward pass to the entire model, just to produce the negatives, right? And okay, on this example, it's two-dimensional blob that is fast, but imagine doing this on, let's say, 224 by 224 images. And so each step is going to take you like minutes, okay? And so, yeah, the problem with that is, well, it's computational cost. Okay, so, well, so what, what you can do here, of course, you can, like, as I mentioned before, you can play with these parameters, so it becomes more efficient. So maybe you can do less steps or more steps. I don't know. Let's try something random here. Let's see what happens. Let's see if I can break it. It still cannot work. But yeah, you will see that in, like, more difficult examples, this is it's going to, well, let's try this. Let's try one step. And let's try something like this. Okay, we start that. It's not too bad. It's still working. Let's try something really big. Oh yeah, you know what I was doing? I was changing the defaults. So let's try, what do we say? 10 steps and 0.1. So you can see it's getting worse now, right? Like it still kind of figure out the valleys, but they're not following the contours yet. And well, you can see that at some point, it's not going to work anymore. And yeah, it gets really hard to find this thing. Let's see. Let's do one step. And maybe this is a very simple case. Yeah, you can see we start to have some problems where it's kind of going horizontal, and there's a bit of up and down, so it's not really it's not really doing that well. And if I increase my step size, yeah, it's kind of getting worse. So just to give you an idea, right? And yeah, so you have to essentially you have to play with these parameters, and it takes there's a computational cost. Okay, so well, what do we do now is let's go with JEPA, the JEPA approach, right? So we have the same data point, but we are going to use a different approach. So instead of generating the negative samples, we create two independently noisy copies of each training point. So let's call it the view of A is the original point plus a small noise, which in JEPA is called the context patch. And B is, well, I take the same point, but and like I add some noise. And this is the target patch. Now, noise means, well, this is random, so you're not going to get the 2 points identical, but they are imagine 2 points, like you have the original point, and it sort of gets away from each other. You split in two. And so the two noisy views play the role of this context patch and target patch in iJEPA, which is the image version of JEPA. And so, like, if you have images, those patches are specially separated into regions, and the masking that you can see here is just Gaussian noise. You know, like you have a sigma of 0.08, for example. And so you have, you essentially have three components. You have the context encoder, which is the trainable part. You have a predictor, which is also trainable. And then you have the target encoder, which is, in this case, is using the EMA. Okay. And it's the exponential moving average and does have no back propagation. So the model gets this view of A and must predict the embedding of B, and not the raw point itself. So the loss function in this case is the mean square error in the latent space. Okay, so it's the Z. Okay, let's not get confused again. That's the latent space. The Z from JEPA is not the partition function, is the Z of the latent space. And so you want to minimize this MSC. Okay, and it's a simple square distance, like nothing fancy. So as you can see here, as I explained, there is no fake samples because you take, I guess you can, I mean, it's kind of like fake, but meaning you do have the original point, which you sort of shake it a little bit, right? But there is no MCMC, there is no Langevin steps, there is no backprop, and this is there's never back propagation here. It's frozen, right? When you calculate the target encoder. And okay, so why do we need this EMA, right? And the reason why we have EMA is that it's the kind of Achilles heel of JEPA, meaning that it's like if you do it as it is, with this kind of learning function, to minimize the loss function, it can cheat, right? So your predictor can say, well, I'm going to predict exactly the same thing I'm seeing. So to make it harder, you sort of introduce this moving average. It's like you introduce like a shadow, right? Like a slow moving shadow of what you can do, what you can see. And so let's go forward and let's see how this looks like in terms of, let's say, processing. So we are going to read this from left to right. So you have your original point, which is two-dimensional. So it's it's X and Y. And you add noise to both, right? So you take the original point, two-dimensional. You introduce noise, which is independent. So you create two, like, let's say, copies. One, you call it the context patch. One, you call it the target patch. The context patch goes through an encoder, okay, which create the latent context, whereas the other guy, B, goes through the target encoder, which produce the latent target. And okay, so you have these two paths, And these dashed curve arrows show that this EMA exponential moving average update. Okay, so the target weights slowly. The target weights here slowly track the context weight, but never receive a backprop gradient, right? So this is stopped. So it's very important. This doesn't backprop, but the predictor is trainable, which gives you the Z that you need. The minimum square error loss, which is green, minimizes the difference, the square difference between the predictor and the target. Okay, so this is EMA only. There is no backpropagation, and this is your loss function. Okay, so yeah, this sounds easy. So yeah, so the purple target encoder is purely a slow-moving shadow. So think of this as kind of a shadow, and you have this kind of asymmetry between the orange and the frozen purple, like these two or these two. Is the entire trick. So the entire trick here is this EMA shadow that allows you to create like something that doesn't cheat when it's trying to predict the B point. Okay, so let's go next. This is a kind of like visual representation of what's happening, because I think this is kind of interesting. So in panel 1, you have the original blobs. So it kind of looks like vertical because now I didn't scale it just to kind of show them better. So I didn't scale them equally, but it's the same thing. So it's two circular blobs. And then what you do is in this panel 2, I just took 30 match pairs. So the circles are what we call A, and the triangles are the B. So the gray lines connect the two views from the same source point, right? And so you can notice that these pairs are very close together. So because the sigma I chose is 0.08, which is very small compared to the intercluster gap. Of course, if you change the sigma to be too big, there's going to be some problems there, because then it kind of gets confused between the two clusters. So yeah, choosing this variance, it's really important, right? And so, okay, so you have this point. So if I zoom in, I just zoom in into some of the pairs. So like you can see that, like, I don't know, between this point and that point, this was the kind of original point. I don't remember. Yeah, I think this is it. Like I try to make it kind of simple to see, and some of them are too close, but essentially you have this jitter, right? So you do like a jitter that separates the original point into two, and well, the takeaway here is that the model must output similar embeddings for a circle and a triangle from the same blob, but different embeddings for pairs from the opposite blobs. Okay, so let me repeat it again. So the job of this model is to give you similar embeddings for a circle and a triangle from the same blob, let's say the blue one, but different embeddings for pairs from the opposite blob. Okay, and well, in this case, we never told the model the colors, right? Because I mean, if you look at my code, I never say, hey, this is label 0 and this is label 1. Like, this is unsupervised. And so, yeah, the model doesn't know there are two classes. Okay, so let's go to my next cell. Don't get scared. What do we see here is where the kind of magic happens. Yeah. Let me explain from, let's say, the top left. So we run this training for 400 steps, which is the x-axis. So you have 0 to 400, 0 to 400. And you can see that I plot the loss function. So this is the kind of loss, and you also do the smoothing of that loss. And you can see that there is some sort of inflection point around like 50. And so, well, if we, why is that? Well, there's some sort of explanation. You have two phases. But let's say that in phase one, when you initialize the context and the target encoder, they are identical copies. Okay. So the prediction and the target, the loss starts very low, right? This is like the easy task. So it's like if you're predicting your own reflection, like you're in a mirror, you look yourself to the mirror, and well, you can say, well, that's me, right? So it's the same thing. So yeah, so they're identical copies, and so essentially, it's kind of easy. But then in phase two, where you have this kind of inflection, so yeah, they're trivially close. It creates this moving target where the EMA lags behind improving the context encoder, so it becomes harder, which is good because you don't want this to collapse. Okay. And so yeah, the context encoder improves the back propagation. So we do have one back propagation, and its weight diverged from the slowly moving EMA target. So the target is now a lagging version of the context encoder. So it's always kind of like a little bit behind. And so the predictor needs to work harder. So the kind of loss start to increase a little bit, which means it's a good thing. And so on the right plot, so the latent spread, it's the mean standard deviation across the latent dimension. It's kind of, you do want to have a spread, because if it's above 0, that means that we have diverse representations. So if this was kind of around zero, that means, well, the representation has collapsed. So like it's not doing anything useful. It's just predicting the same point. And well, you can do our good old friend principle, the PCA projection, which is, once again, this is just the pure JEPA. It's kind of the payoff. So even though labels were never provided, the kind of learned latent space cleanly separate these two blobs, right? So I did the principal component analysis on the latent space that was learned through the back propagation, but not, remember, this was not from the Langevin dynamics. This was purely made on the trainable predictor with this loss. Okay. And anyway, so let's go back here. When you do the PCA analysis, you can see that it's kind of a sanity check. Like, hey, actually, yes, there are two distinguishable areas which match the colors that the model didn't know. So wow, so that works. Essentially, you know, this thing is working. So now we have some questions. Why the loss here? You can see that is going up a little bit. So why this? How do we know this doesn't increase forever, right? So will this just be climbing up? But the answer is no, for three main reasons, which I sort of explain here. And well, the first reason is the EMA convergence. When you choose tau equal to 0.99, the effective time constant is 100 steps. So once the context encoders Adam update shrink, as it converges, the gap between the two encoders closes exponentially fast. The second reason is the noise floor. So each view adds this independent Gaussian noise of 0.08. And like there is no predictor that can overcome this uncertainty. So there is always, what should always be a hard lower bound on the achievable loss. And the third reason is bounded weights. So Adam keeps parameters in a bounded region. So bounded weights means bounded representations, which means a bounded mean square error. So there shouldn't be any runaway mechanism. So the next cell extends training to 1,000 steps to show this empirically. And let's see what we get. And yes, we can see that, yeah, it was kind of increasing, but then there is some sort of a plateau here, right? Where essentially the EMI target has caught up and the loss stabilizes. Okay. And so the red dashed line is essentially like, you know, where we stopped before. And you have this, the kind of green plateau is where it sort of stabilizes, which is around 15, plus minus 15 of the median. And well, the loss essentially flattens and stays flat. So yes, so it's a little bit higher, but essentially it has stabilized. Okay, and this should always be the case. Then the question is, well, when should I stop? And well, I'm not sure how do you do that. I think it's maybe this kind of one of the papers, but we can investigate that later. Okay, so what do you think about this, right? So we, you know, think of this in terms of computational complexity. You know, you had, you know, we're doing, you know, this, what you're doing here, it's a toy, right? But, you know, if you think of putting this into full-scale models, there are like two very important problems if you're using Langevin dynamics on images. So problem one is cost. So every Langevin negative requires 40 times forward and backward through the model. So if you think you have a 224 by 224 image, it's probably around 150,000 dimensional input space because of those like, yeah, as you multiply that one, and like imagine now you go to video, and you know this, like, you know, video you have frames, so you have time dimension, this, you know, this cost goes high, and so it's not practical at scale. And the number problem, so the first problem is cost, is scalability. So the energy landscape is high dimensional as well. And like in the pixel space, because remember that Langevin operates in the original domain, it's really, how can we say, rugged. So the Langevin mixing is low. So these kind of chains never properly leave the local minima. So the negatives are poor and the kind of training destabilizes. And like you can try, I mean, maybe I'll do another tutorial where I can actually show you that, you know, if you apply these to images, yeah, it's really hard, almost impossible to make it work. So, well, the solution which is why this is very important, is this JEPA approach, where you work in latent space. So you have typical dimensions. It's maybe you can operate at 256, 4096, in terms of the latent space, instead of the, let's say, 150,000 of pixel space. You have a kind of a very nice move and dense gradient that give you a better signal. And also, as I mentioned before, you have kind of like with JEPA, you have a sampling free approach. Like you're not really doing sampling, right? Because, yeah, as I shown before, you take this point, you split it into two, you do that trick and calculate this prediction error. So yeah, this is the trick. I mean, it looks like like really, really, I guess simple, but yeah, that's what it is. And so think of this kind of latent space as kind of like a language of, I don't know, I wouldn't say brain, but some sort of cognitive process. Whether, like, if you see a dog or hear a bark, the latent representation encodes the same concept. And so, okay, so like, what's the JEPA revolution? As I mentioned before, so you solve the energy collapse, not by pushing up fake data, but through this constraint. And the constraint is this stop gradient. So we don't train the target encoder via backprop. So remember this, the target encoder is frozen. So it doesn't move, right? As you can see, you can check the code, there is no backprop, right? The backprop is on the predictor only. Then you use the so the point of the stop gradient is to prevent this collapsing, okay? Because, well, what you can do if you want to cheat, you can just can set both encoders to 0, right? Like, set both them to 0, great. I have a 0 loss. The EMA update. So the target weights are a slow moving shadow of the context encoder, and they always lag, I don't know, let's say 100 steps. And that lag is this asymmetry that forces the encoder context to keep changing. In fact, if you disable that, you will see that it's not going to work anymore. And then the third point is this the L square, so the distance function in latent space. There is no energy traversal, there is no Markov chain, it's just the gradient descent on the predictor weights. Okay. And okay, there is, like some kind of a little bit more like an explanation here, is that although Lecan frames JEPA in an EBM context, when you look at the actual implementations like iJEPA, which is for images, and vJEPA for videos, they do not use Langevin dynamics. Okay, I mean, you could use it. I think you can use it, but it's not going to work essentially. And JEPA is not a better implementation of Langevin. It's just a different problem formulation. Okay, so it's as you have seen, it's very different. It's a very different approach, right? It's not like, hey, I took the Langevin dynamics and I sort of optimize it. It's totally different. Okay. And what else we can say? Well, there are some things kind of interesting, as I mentioned before, is this the ReLU and the CeLU, which was my default. And the reason why we're using these CeLU units is that it gives you like a smoother activation for stable learning. I guess you can use the reloads, but it's to be less smooth. Or you can do like without EMA update, and you should see that collapse. I mean, you can play with this code, and you can disable that. So let's do that. So what I'm going to do, I have some sort of like free cases now, free variants on these toys, and essentially, what I did here, I changed it. So instead of doing the two blobs, I'm using a sinusoidal signal just to kind of make it easier. So you have the naive version, which is the essentially there is no JEPA. There's just the target encoder. The target encoder in this case is the context encoder itself with stop gradient, but no EMA lag. And so what you can do here is you can see that the MSC goes down, and you think like, wow, this is great, it's going to 0. Like you think, wow, this is amazing. But actually, if you look at the spread, the mean of the standard deviation of the predicted latent dimensions also goes to 0, which means that the spread goes to 0, means that is basically collapsing to the same constant. So when you look at JEPA papers or methodologies, you need to always look at these two charts, because it's not like, let's say, traditional machine learning where you look at the, I don't know, train loss, validation loss, and you compare them. You have to look into these two, let's say, dimensions. In the second case, I take the, let's say, the original approach, but with the EMA. So essentially, we introduce that link, the exponential moving average, and in this case, well, you can see that is the MSC increase, but the representation spread is going up, right? Here we go. This is here, so it's what that means is working, right? So it's not going to 0, and is going up, which is a good thing. And then I replaced the silo unit, so which was the original code, which is the practical default, and you can see that it gives you kind of like let's say smoother gradients, and with EMA gives you kind of like a more stable run, essentially, right? So it goes here, and like the representational spread is a little bit lower, but while the MSC is a little bit high. So yeah, think of that. Yeah, so both variants work. They have some pros and cons, but of course, if you disable this trick of the EMA, you are not getting anything useful from that. So that's the story here. So the energy collapse, this is the Achilles heel of JEPA. And essentially, it's like reward hacking with reinforcement learning, where essentially the model short circuits itself by mapping every input to the same constant vector. So like you have an input, like any input goes to number, I don't know, 5 or 42. And so basically the loss goes to 0 and the representations become useless. And so, like, very importantly, so I'm going to repeat this again, the EMA stop gradient prevents this because the context encoder has an incentive to produce different representation or diverse representation, and the target is trying to match kind of a lagging, more structured version of itself. So if the context collapses into a constant, the predictor still needs to match a target that has richer weights. So in that case, you kind of create this kind of like a contradictory gradient that push context away from constant output. So it's a strategy to kind of move it away. And as I said before, so you use the latent spread in the naive plus relook as a diagnostic. So always remember to plot both charts. So if the spread goes to 0, that's bad. It's collapsed. If the spread is more than 0, you have got something interesting, like representations. So to close down this tutorial, and maybe I will do another one, is, you can go and read the original papers, so like the one from 2022. This is essentially explains the EBMs, JEPA, and the path to autonomous machine intelligence. And then, you can go and read the iJEPA, so you have Joint Embedded Predictive Architecture for Images, which is kind of like what I did today, simplified in a few lines of code. And then you have the video JEPA, which is essentially the same EMA, but plus they add the masking recipe. And you can see how this, because you have time, right? So like you can see that this approach scales to very well to temporal data without Langevin. And there is another one, which was the intuitive physics from JEPA. And this is where they start to talk about word models. So essentially, the latent model represents physical reasoning, essentially, right? So you can learn concepts like gravity and object permanence in the latent space. So I hope you enjoyed this tutorial number 2. You can see the code at the bottom of my YouTube link, and feel free to play. And maybe in the next tutorial, I will do either some sort of maybe a simplified version of the image JEPA, like really, really simple, so you can play with that. And I think I'm going to do it with the Langevin dynamic and without, just to kind of see how this change. So I hope you enjoy this and gives you a better understanding of JEPA. And so let's just see you in the next tutorial. Thank you very much.